Well, good afternoon. Thank you very much for coming. My name is Terry Pass. We're here to talk about big data and analytics around energy and management of that energy. My name is Terry Pass. I work for Netapp. I'm their Senior Data Center Integration Architect. That's kind of a buzzy word, but it basically entails that I do the architecture and engineering and deployment all of our data centers, all 10 of them worldwide, across for delivery. And then I also build all of our tool suites for that delivery. So anything going in or out of the data center from a configuration management perspective to our service catalog that delivers our self-service portal for internal data center cloud and external data center cloud. So that's kind of my background and what I'm here for. Netapp also delivers a product we call our auto support system. That auto support system receives messages from all of our install base on a weekly basis. Each day we receive logs, we receive configurations, and any kind of hiccups that may happen on those devices. During those weeks, every week that we receive that data, we receive about 1.3 million mail messages a week. Each mail message within 2 minutes is processed through our system, and we put it into our CRM system and create a ticket for each one of those. So our customer base has the ability to go into our front-end portal and look at that data and see how many tickets they have for their particular systems. Because of that data, we have about 7 terabytes of data that comes in a week, and that's about I said terabytes. I said 1.3 million messages, about 1 terabyte worth of data on a weekly basis. So every year we grow about 7 petabytes of storage a year, and then we have to increase that our system to support that about every 16 months. So that system is put onto a Netapp proprietary system on a Hadoop cluster, and what we do is we use a 48-node set of clusters, and we deliver those with 12 E-series hosts, and each of those are tied together, and this is where the data is poured into on a weekly basis. So without further ado, I'm going to start talking about introduce our first panelist, Omar Sadidkou. He's a senior technical executive at IMPRI. If I said that right. Electric Energy Research Institute. Mr. Sadidkou.
Electric Power Research Institute.
Electric Power? Okay, fine.
Close.
Mr. Sadidkou provides leadership and help to his R&D team to accelerate advancements of technology, enables cost efficiencies and environmental sustainability for energy use. He consults with the energy power systems and the government officials on energy utilization. Our next panelist is Alan Daly. He's the co-founder and vice president of engineering at Brightbox Technologies. Mr. Daly particularly has particular expertise in controls, energy modeling, design, energy flow, and high energy buildings. He's served on several boards for committees such as Berkeley's Center for Building Environments and the U.S. Green Building Council Lead Energy and Atmospheric Technical Advisory. Our last panelist is a substitute. Ram Rajagopal will not be here today. He's off in Brazil, probably watching the game. But Dr. Sam Borgstein has agreed to step in for him. Mr. Borgstein has a co-founder of a San Francisco enterprise company that creates software for developing new enterprise companies. He works here at Stanford at the Sustainability Lab, creating meter data analytics and performance metrics. He's developed a statistical model to estimate information about building stock, and the resulting information has developed empirical methods to support planning, targeting, evaluation of energy efficient and demand response programs. So without further ado, let's have Omar come up and provide his presentation. So what we're going to do is we're going to let Omar present his, and then we'll take a few questions after, and then we'll move on to Alan, and then we'll move on to Sam. Thank you very much.
Great.
Perfect.
Okay, good. Can everybody hear me? Excellent. Well, it's an honor to be here this afternoon to address this group. I know we've all heard really remarkable presentations this morning and through lunch, so I will try to live up to the lofty standard that's already been set. It's an honor to be here on this panel. Terry, thank you for that introduction. Big data, it's a term that's become so commonly used that the meaning of it is starting to, I think in some circles, sort of lose resolution. I think there are as many big data conferences that are available to go to every year as just about any topic, certainly in the energy field. What I'm going to talk about is primarily some of the reasons from a utility perspective of why there's interest in big data, particularly on the customer side as it relates to using that as a means to better understand customers and customer behavior, and as I have here on this introduction, to enhance the utility customer engagement. So I'm really going to talk about some of the reasons why, from a utility perspective, we're interested as an industry and we care about wanting to use this big data. I think some of my panelists that will follow will talk a little bit more about the how in terms of hardware and systems and devices and methods to tie it all together. So I think in totality it should be a good session. We're looking forward to your comments. Let's see if this works. Oh, okay. EPRI, we're headquartered right nearby. I see a couple of my colleagues here in the audience as well. Our mission is really to advance research and development for the industry to help keep electricity safe, affordable, reliable, and environmentally responsible. And our research covers the whole spectrum of electric utility operations, from nuclear and fossil generation to renewables to transmission, distribution, to the area that I work in, which is called energy utilization, which is the research that touches how electricity affects end users. And really, as shown here, there's a cluster of research that spans this area that we call energy utilization. And really, we have here at the bottom load analytics and behavior. And it's an element of our research, but it really ties into all these other aspects of our research, certainly with energy efficiency and demand response, which I'm going to talk about, along with these other areas that, again, affect our research and how the end use of electricity can be used more efficiently overall. So really, that's kind of the framework to start this off. So from a utility point of view, there's certainly an interest in understanding customer usage profiles. I mean, when you think about it, you can go back to first principles. Utilities, for the most part, it's a very regulated industry, and really, they're, recouping the fixed costs of delivering that power are really tied to customer usage. And so utilities are interested in, the quality of the data that they're able to, in the quality of customer data, particularly how accurate and how extensible, how much it can be used more broadly. At EPRI, because we try to serve, what our utility, clients, what the industry is looking for, we recognize that there's a need to come up with methods to investigate, how to more cost-effectively not only collect but also measure and use end use data to provide deeper insights. And there are a number of ways that we're looking to go about this. Certainly, and that's really the bulk of the topic here for this session, is how to use data from AMI, from advanced meters, to go about and infer deeper insights into customers. There are a few other techniques that we're also looking at to look at end-use data, including methods to look at non-intrusive load monitoring devices that can disaggregate whole customer data into constituent end-use parts, and also low-cost sensors to enable that to be done more cost-effectively. So when we look at the applications of customer data, we've come up with a list of sort of a top 10 list of applications. And among them, excuse me, using customer meter data to help provide measurement and verification insight into energy efficiency as well as demand response. Among the other things that we're looking at, customer segmentation, customer program design. Okay. Excuse me. So there are a number of applications in which customer meter data can provide insights to the utility. So one of the things that we're looking at here is how customer meter data can be combined with other sources of inputs, including weather, other inputs on buildings, other publicly available insights on customer uses, to be able to provide insight into how energy is being used in a more detailed manner. So there are a number of industries and types of service providers that have come onto the market that purport to be able to take end-use interval meter data and couple that with basic factors of the type of building, the size of building, or customer premise, to infer insights into not just how much energy is being used overall, but how much is being used by end use at any given period of time. And there are other applications for which that can provide even deeper insights. So for example, one of the things that we're looking at is, can investigation of just the meter data provide insight into how much customers have been participating in energy efficiency programs, and for that matter, demand response programs. So if there is one of the things that we're looking at is, and we've done research looking at, can analysis of just the meter data be used to infer whether customers have participated in demand response if they signed up for a particular type of program, to see results at the end use level. It can also be used to look at whether, using meter data, if we look at item number 5 there, to see whether equipment, if you can look at, infer a participation at the end use level, whether equipment is performing up to nameplate specifications. And if not, to provide remote equipment diagnostics. This is generally known as continuous commissioning. And this is an opportunity for utilities to provide enhanced value-added services to customers and improve their relationship. Distribution planning, one of the opportunities here would be, for example, being able to infer from meter data whether there's a large concentration of, say, electric vehicles in a particular distribution a load pocket. And that can help to provide insight into whether there's a need for upgrades into transformers and other infrastructure to help sustain what could be projected growth at that small circuit level. Rate structure design, to look at and better understand how and when customers are using electricity, can help utilities provide rate structures or electric service plans that can better meet the needs of those customers. And ultimately, what utilities are trying to do is better understand what motivates customers, how they're using electricity, and how those usage profiles are changing given new technology and choices that customers have at their disposal. So again here, the measurement and verification opportunities from meter data analysis is just one of a number of the potential uses of big data. And as I talked about here, again, the opportunity to look at continuous commissioning and to verify participation in programs is also a large opportunity. When it comes to electric utilities, there's been a disconnect over a period of decades in having closer insights into what makes customers tick. And there's an opportunity to use big data, meter data analysis, coupling that with insights from the social and behavioral sciences to better understand how to segment customers and then how to provide distinct types of offerings to them, whether it be offerings in energy efficiency or demand response programs or other types of electric service plans. So this is really one of the, these are some of the areas that utilities are interested in. So among the challenges, and this really kind of sets the stage for sort of the panelists to come, there's been a lot of focus over the past decade in AMI deployment and in getting smart meters out there, but not as much on how to use the resultant data. There's been a lot made in the past few years about the Green Button Initiative here in California and in other parts of the country, and the opportunity for application providers, third parties, to take your data with your consent and use that to present to you, the customer, better insights so that you can make more informed decisions, knowing how much electricity you're using. That's also another useful benefit of having this interval meter data at one's disposal. But from a utility point of view as well, to look at this, there are issues around how to just manage and store the sheer volume of data, looking at also data security, privacy issues, and so forth. And so from a utility point of view, the issues are around what kind of infrastructure do I need to support this endeavor, what kind of means to acquire and process and store and ultimately convert that data into actionable insights, and what service providers and the whole ecosystem here of hardware and software providers are available to provide those types of solutions. I think utilities are in a state of overwhelm in some respects with the choices that they have available to them. And again, this is kind of a continuum of the types of resources and the framework to take data ultimately into the plane of applications that can actually serve them and end-use customers. So among the questions that utilities are grappling with is what is the they're trying to lay out some of the applications, potential benefits of big data from a customer energy management standpoint. There are issues around, well, what's a suitable granularity of meter data to provide those types of insights, whether it's at the second, 15-minute, or what can be done just even with hourly data. So that is, these are really some of the questions that utilities are grappling with in trying to understand how big data analytics can better serve them and ultimately help the customer utility engagement. So with that, I don't know if I can take just one or two questions now.
Yes, you can.
Or then wait till.
And are there any questions from the audience? We have one down.
My question is EPRI considering adding to its mission the security of the energy supply?
The security of the energy supply?
That's right.
I mean, the security of, could you elaborate on that?
So recently, a power station was attacked. I can't remember exactly the details of how, but
PG&E.
The answer to the question is yes, and EPRI would get considered.
It's great to have EPRI alumni in the audience. Yes.
Could you talk a little bit more about making the jump from providing more information to consumers to actually getting them to change their usage habits?
Okay, so I was asked to repeat questions. So talk a little bit about the jump from giving consumers more detailed information to actually seeing their behavior change. Was that the gist of it? Yeah, that's a great question, and we have a whole area of research looking at that very topic. There are a number of drivers to affect how customer behavior with respect to how they use energy. So it's not just what information is presented, but it's how it's presented is also a very big issue. I mean, I think all of us here in the room are probably familiar with O-Power and companies or service providers of that type that really look at taking data, and even there, we're not necessarily talking about big data. We're not talking about interval data, but presenting your overall usage in a way that compares it to some benchmark that's meaningful to you, and that ends up being something that they found to be a very strong motivator. So it's a burgeoning field in the utility industry in bringing in some of the social sciences and behavioral sciences insights. But the general idea is the more detailed information that you can give in a way that doesn't overwhelm the customers, but that really does provide meaningful insights so that they can correlate changes they make from from a hour to hour, minute to minute basis and see what those results are as far as a reduction in their bill. That's where you see, where it becomes more visceral. The idea is that, makes that more of a compelling, makes the data more compelling. Yes, sir.
Thank you very much, Omar. I want to move on, and then we have a question answer at the end as well. So, thank you very much, Alan. Thank you very much, Omar.
I think there's some spots.
Is that good?
Oh, thanks. Okay. Okay, hi everybody. My name is Alan Daly, and I'm going to give a little bit of a different style of talk, I guess, today than we've seen so far. This is a little bit more kind of from the trenches. And I think maybe the idea was when they invited me is to just talk about some ways that this company I've co-founded recently called Brightbox Technologies is actually using data to save energy. I'm an engineer. I've been a HVAC engineer working as a principal at Taylor Engineering for the last 15 years. And I spent a lot of my time out sitting in buildings, watching them get built, commissioning, working with controls contractors is really one of my specialties. And realize that controls matter, no doubt about it. I can be sitting in a building, sitting with a controls tech side by side, and as we get that system tuned up and working, I can watch the power go down. And if I hadn't showed up that day, it would have still been high, and if I'd left the building, it would have been working fine. But when it's commissioned and controlled correctly, you can do substantially better operating a building than if it's just left as it is every day. So this company, the idea is to try to deliver this advanced control in a way that is scalable and pervasive, and we can get into existing buildings and actually make a difference and save energy with data. So we are a software-only solution. The idea is we're only controls. It's a software web application that connects to existing buildings, gets a bunch of data. I'm going to talk today a lot about how, what data streams we use, how we use it, and how it all gets put together. And hopefully that'll spark your imaginations about what uses we can have for big data in buildings right now. We reduce operating costs, we reduce energy use, we can reduce peaks, and we can, most importantly, improve control and comfort. So we actually make the buildings work better at the same time as we make them save energy. So what do we do? What's our approach? We use this technique called model-based constrained predictive control, often called MPC. The idea is that we're building thermal models of buildings, analytical models, differential equations, hooking them all together so we understand what's connected to what and how those pieces of equipment behave. We then use lots of data, and I'm going to talk about that in the next couple of slides, about how to characterize those components, how to learn their behavior, so in the end you have a very well calibrated, very well characterized model of how that building's operating. We couple that with then best-in-class basic controls, heuristic controls we call them, and we have put this all together into a platform that makes it all work. That graph on the right there is actually one of our models in a nice 3D surface plot about how a packaged AC unit from the roof of a building might work. It's kind of cool. So what does it do? Model-based predictive control, or MPC as it's sometimes called, is everywhere, except for buildings, unfortunately. It's used in self-driving cars. There's a lot of discussion of that in the last session. UAVs that deliver books to your door one day soon are all controlled by MPC. Process control, industrial control, refineries, laser cutters, aviation, it's everywhere. It's the industry standard for controls, except for buildings, for some reason. We're just slow to adopt in our world. And so what we do is we have got basically a cloud application over here on the left, and our application runs up here. We connect into the existing building control system with some software that's resident on the software controller in the building, the server, and it calls out and sets up that communication between the two. So it's a very light touch in the building, and then plugs into our cloud application. The first source of data that we use is actually the existing building controls. We like to go into existing buildings, right? There's lots more existing buildings than there are new ones. We can go in there, and if there's an existing building control system in place, the first thing we do is scrape out all the data that's in there and suss out as much as we can about what's connected to what and how it's all configured. So we are able to build our models of these buildings quickly because we are starting from a good set of data that's already there. The next source of data that we use is time series data. So once we make that connection to the building control system, we're continually pulling out data about what's happening in that building. And we then use the data streams and plug them into our models of the equipment and get these calibrated curves. So the dots here are all different operating points, and then the red line here is us building a model on top of the data we've collected to have now a good sense of how the fan curve looks for this one unit. So we know now when we want to blow 15,000 CFM, how much power we're likely to use, and use that in our optimization later on. So we're using data about the building control configuration, and now data about the system performance in real time. We also build models of how the building is used. It's hard to see this graph, it's a bit of an eye chart. But what we do is collect the thermal behavior data of just temperatures, right? Temperature data, and we plug it into our thermal models and our differential equations and understand zone, that person's office on the 3rd floor usually heats up and cools off like this. Today it heated up and cooled off a little bit differently. There must have been a load there. If the sun was out, we know it's a solar load. If there was no sun out because of our weather data we've got, we can detect that it was a plug load and start to build load models so we can then predict into the building about how that building's going to be used by the occupants. We also collect lots of weather forecast data. We plug into NOAA and other sources for weather data, and we've actually started collecting databases, collections of forecasts, not just of data. So we can actually tune up and say how good the forecasts are for certain areas and use that information about uncertainty to help influence how we control. But we're plugging in weather data as well into our system. Lastly, and following on Omar's talk, we're using all sorts of smart meter data. We love the fact that this data is available to us. We're actually doing techniques where at night, when the building is sort of dormant, there's often some base load, but we can find flat spots. And during those flat spots, we're able to excite the equipment because we've got this connection to the control and deduce out then the performance curves for that equipment, even though we don't have sub-meters and other expensive stuff installed in the building. So we're using smart meter data in really aggressive ways. And we're also using it for all of our M&V and things like that. We're also plugging into national databases like the NREL National Utility Rate Database. This data is out there, utility rates for like 2,000 different utilities in the country. Plug it in, it's all free, amazing resources that we start to pull together. And this is really important because right now in building controls, those of you that know buildings, where in the building control system do you ever enter in the utility rate? Doesn't exist. There are no dollar signs anywhere in the existing building control systems. There are a couple exceptions out there. I see a couple of people going, oh, we got a better mousetrap. But in general, you do not plug in dollar signs or utility rates anywhere. But what owners care about and what drives our market approaches here is dollars, right? So we build in the model of the utility rate. We then feed that to our analysis as well and try to minimize on cost, not just energy. The result is that we do a very good job then of being able to predict what's going to happen. And without going into the details on this picture, on the far right over there, you can see this is one of our kind of test buildings where we had some sub-meter data where we instrumented to validate our approach. The yellow line and the blue line match very well. And the yellow line is basically created based on our models. The blue line is from real sub-meter data, so we can predict very well how these buildings are going to perform. What do? We then feed these models, these well-calibrated models, as well as weather predictions and load predictions and utility rates into our optimizer and say, for the next period of time, 24 hours or 6 hours, how do we adjust all the system set points to minimize cost, minimize energy use, improve performance, and use an optimization approach. One of my co-founders is a guy over at UC Berkeley named Francesco Borelli. Francesco is just great with optimizations, and he's a real expert in MPC. And this is all his side of the world, so you can't ask me too many hard questions on this stuff. But the optimization basically then finds the next approach, and we're doing this every 5 minutes. So we're continually collecting data, continually adjusting, every 5 minutes, looking out over the next set of hours, and then sending back optimized set points in that 5-minute time frame. We tackle some pretty tough problems. Our largest installed site right now is this one. It's 4 buildings, 8 AC units, 2 on the roof of each building. 385,000 square feet, 600 VAV boxes, for those of you guys that know what VAV boxes are. Each unit, we collect 22 signals. Each space, we collect 30 signals, actually. So together, that's 18,000 signals that we're collecting every 5 minutes. Over a typical 12-hour day, then, that ends up being about 2.5 million data reads that we're doing to monitor the operation of that building. In the last talk, Stephen Heck said that if you were sitting there watching, driving your Prius and watching on the right and really trying to optimize, you could get about 10, 15% better. That's what we're doing. So we're continually doing that for you, whereas a human being, if a human being was sitting there optimizing, they could probably do as well as we can. Maybe better, probably not, but maybe as well. A really experienced one. But nobody just sits around and twiddles knobs in today's world. Just people are too busy and there's too much pressure for salaries. So we do that for you. The result is that we see in some of our best cases as much as 25% HVAC, maybe even more in some cases, 25, 30% energy reductions on the HVAC systems that we're controlling. That translates often to about a 10% overall whole building approach, whole building cost savings. And you're seeing a little bit here some of our M&V that we do, where we compare a red baseline to the green actual measured performance. There are days here where we can turn our stuff off. One of the most interesting things about a software-only solution is that we can turn it off. And we can check our baselines and see where we are. So when we turn it off, we look great. When we turn it on, we do even better. And we're able to kind of get some sense of what's going on there. So, is it that order of magnitude that Stephen Heck was asking for in the last session? No. But is it relatively straightforward to get and cash flow positive and a nice way to save energy and make your building better, right? Because the other piece of this is that we're actually improving the control as well. This is temperature bins of temperature violations. So if your set point is 75, but it actually goes to 76, we call that a 1 degree violation. We average them out. Under the baseline control, the oranges are there, where we have lots of excursions. When we turn on, we get blue, tighter control, and still saving energy. So it's a very powerful combination by having this model-based approach. Lastly, it's really cool. Our models are so good that we're able to do things like send it a constraint. Package unit 4, do not use more than 10 kilowatts. Boom, put that constraint on. And then here's the resulting power, flat. This is the control signal that comes out of our system to make the unit behave in that way. And we have very rudimentary knobs to turn. We can just tell it what supplier temperature to make, right? So we tell it to not use more than 10 kilowatts. The supplier temperature goes up and up to keep those compressors off. We then say, okay, you can now use 25 kilowatts. Supplier temperature comes down, the compressors start to come on, we start to use power, put the constraint back on, take it off, watch the whole thing work. This kind of a control signal coming out of a system is, you don't see that anywhere in regular building controls today. We're able to really make these systems dance with this kind of control. And the question is really, what do we want to do with it next? Where do we go? It has implications for smart grid interactions, has implications for demand response, energy, comfort, all sorts of great stuff. So we're just starting out. Our company is relatively young, and we're about our first year in, so gives you a little bit of a sense of what we've been doing, and maybe, like I said, spark some imagination about how to use data to really save energy from the trenches in buildings.
Thank you, Alan. We probably wrote. I think we have time for at least one, maybe 2 questions, if we can keep them short. Yeah. Can you use the mic or holler out?
Or just, yeah, I'll repeat it.
So how does your app interact with the on-premise controls?
The question was, how does the application interact with the on-premises controls? What we do is we drop a little bit of software into the server, and that sets up a communication link with our central system. We've taken the approach to work very closely with manufacturers rather than to keep them at arm's length. So we've identified one manufacturer we're working with now. We have technology development agreements in place with them. And so we're a very open, very collaborative relationship with these manufacturers. They love this stuff because it makes their products look better. So it's a piece of software we drop, and then that sets up the interaction. One more quick one?
Yeah, I'm looking at your data. It strikes me like it could be deterministic chaos. Do you know what that is?
No.
That means when you have a set of nonlinear differential equations, you have an infinite insensitivity for the initial condition. And one of my colleagues at Emory, John Springer, actually published a book on this. and it's extremely difficult to make a prediction like you're trying to do over a long period of time. Have you run into problems with instability of?
Yeah, we're constantly updating our predictions, right? So we use a shrinking horizon kind of approach, where in the morning we'll predict out over a whole day, and as the day goes on, we're using that continuous feedback to update our predictions, so that by the end of the day, especially as we get to the hotter periods in the afternoons, the horizons are shorter, the uncertainty goes down. I'm not the analytical expert in our group at all. Francesco and his first PhD student, Yudong Ma, are really pros at this, and they would be much better at answering your question than I am. I'm sorry.
Well, you've got more time. I mean, you just started, right?
Exactly, right. I can say that the results we're seeing are real. So I don't know if there's maybe a theoretical problem with what we're doing, but at least we're saving energy, which feels good.
Thank you very much, Alan. Now we'll hear from Sam.
You didn't do that quite right, did you? Yeah.
Shuffle.
It's a little tight in here. Just keep moving around. Shuffle.
Hi, greetings. I'm Sam Borgeson. I'm standing in for Ram Rajagopal, who couldn't be here. He asked me to send his regards. He is, in fact, in Brazil, which is where he grew up. So it's not, and he is working, I can assure you. I got a phone call at 10 p.m., which is like 1 in the morning last night for Ram. But these are his slides, so we'll get the benefit of his wisdom. I'm going to talk to you about the Sustainable Systems Lab at Stanford. This is Ram's research group. I've been a contributing member for several years, originally as a graduate student, and now in this more narrowly defined role, trying to help find ways to marry the insights that we have from the lab to real-world applications. That might include commercialization, but it's not the only way that we think about making a real-world impact. So the vision that really drives the work in the lab is thinking about what are the missing pieces that we need to deliver a sustainable grid. And I think it probably comes as a surprise to very few people that a sustainable grid, if it's defined as having really high levels of renewable energy, has really significant integration problems that haven't yet been completely solved. And they revolve around the fact that renewable energy is imperfectly predictable and imperfectly controllable. And sometimes it's predictable in ways that we don't like it ramps down really hard if it's solar going into sunset. And so the goal of the lab is to address these problems through improving forecasts with things like better data collection platforms, and improving our understanding of the demand side and mechanisms to control and to make demand more flexible through data analytics. And so I'm going to give you some examples from each of those, sort of the data collection and the data analysis that's coming out of this group. One really exciting project that's really just in its formation stage is the deployment of mobile autonomous sensors to improve the resolution of data that's being used as the input into predictive models. And so we have a collaboration with an organization called Sailors Energy. They predict wind for sailors, very straightforward, obvious need that sailors have. But it turns out they're actually, as you can imagine, they're actually pretty good wind forecasters. It's important to that profession or that recreational activity. And what's interesting about this is the current practice. You could probably conjure up in your mind a tower with a set of meteorological instruments on it, a Met tower. But those towers cost something to deploy. You can only deploy them on firm ground and under the right conditions. And so from the perspective of one of these forecasting models, those sensors are sparse. And we're probably not going to solve that problem by deploying Met towers everywhere for cost reasons, aesthetic reasons, lots of others. But what we've found is that the models can actually tell you where spatially the biggest source of their uncertainty is. And so if you feed back the results of a model that's using the stationary towers, you can actually deploy a mobile sensing platform to go and solve the worst problem in terms of the uncertainty in your prediction. And if you have another platform, you can send that one to the second worst problem, and so on. And so the lab is collaborating with some hardware people, and as I said, with the Sailor's Energy, on platforms that are fairly cheap to deploy. They're obviously temporary in terms of where they are and how they're operating, but we have unmanned aerial vehicles. The sort of grainy picture in the middle is a picture of it's a MET station that's hung from a kite. That you can, so you can just sort of fly your MET station, deploy it. And this is part of a trial. I think the expectation is that it'll be more the autonomous drone model that carries the day. And the important thing is that this data is actually expected to cut the model error from these forecasting models in half. And so if you think about this in the context of energy markets, what we have is forecasts from the far future, and then from the closer and closer future, and then from right around the corner of what, for example, wind conditions are going to be. And there's a market for the power that's coming out of all generators, including the wind producers. And so there's really significant cost impacts, both in terms of the need to have reserve operators, people who are on basically speed dial that can ramp up their system if your wind doesn't deliver. And so the uncertainties in the forecasts have real costs to real consumers. And of course, the more renewable energy you have, the more you're going to pay in some sense for those uncertainties. And so this modeling exercise actually has very important real-world impacts in terms of the cost of delivery of renewable grids. Another area where we're focusing a lot of attention, and this project is much more mature and further along, is looking at how do we understand the nature of the demand side of the grid, right? Because of physics, the grid has to match supply with demand at all times. And the traditional way of managing the grid has been you take demand as a given and you just manage the supply. And what we do know about demand comes from things like efficiency programs. And the way that we learn that is often with relatively few people being surveyed or being grouped into what marketers describe as psychometric categories, things having to do with their income, where they live, the climate near them, and so on. And with that sort of hazy view of expectation about consumption, we've built up some infrastructure to estimate how those people will respond to different offerings, for example, from efficiency programs, how to perhaps group them together into groups with beneficial characteristics, how to think about them in a time dimension as well, when they're going to be consuming, and so on. But of course, when you have a resource like a nearly 100% penetration of smart meter data, you basically have as an empirical fact how people are consuming, right? You can access that information. And so we've been looking at ways of not necessarily replacing survey work and psychometric work, but certainly augmenting, and in some cases quite possibly replacing that type of process with an automatable process of meter data analytics, right? And so this is where large data sets come in to this particular kind of work. So one thing that's really nice about this data is if you're doing it right, you have information for everybody. And so it really becomes a question of what can you learn about every individual consumer that would benefit the outcome globally. And the way that we describe that in the abstract is we're extracting features of consumption, which is really anything that you can compute based on the input data that have some value to somebody thinking about dispatch or demand response or energy efficiency or behavioral science or really basic questions about the nature and distribution of energy use. So armed with this sort of more empirical approach, we can develop many of the same things that we have based on survey data and rules of thumb and so on, models of how people will behave, algorithms that can group people, algorithms that can tell you whose door to knock on first, who you most want to enroll in a program and who you least want to enroll in a program, and so on. And we can also take what we learn from trying those things out and feed them back in through a learning process so we can actually improve which metrics, well, we can do two things. We can determine which metrics we extract have the most explanatory power in different situations, and we can improve the metrics that we have, looking for ones that will deliver that explanatory power. And so all of this is present in various research publications, in sort of distributed throughout all the people who are working in the lab. But what we're currently doing is we're engaging in a process of rationalizing it, bringing it all together, making it a platform that is deployable outside of the lab in non-academic contexts. And that is this system to do visualization and support demand operations and management through these data analytics. And so we're happy to talk about any level of interest anybody has and how that works or how it might be used. We're very excited about pushing this stuff out of the university and into the hands of people who can actually save energy with it. One example of the kind of insights that we gained, this was something Omar mentioned. In fact, I was so thankful that Omar is on this panel and preceded me, because he basically teed up a lot of the problems that we think are the important problems to go after, that are both addressable and important to address. And one of the ones that he mentioned was talking about load shape analysis, thinking about what is the pattern over 24 hours of the day that people are expressing, or what is the pattern that's expressed by people's energy choices, right? So the aggregate result of residential consumption tends to be this sort of, I have a plot here that is 24 hours in a day. This is usually what the utility sees, is this aggregate demand. They see a kind of a blip in the morning. This is, your mental model. People are getting up. They're getting ready probably to leave the house for school or work or various things. They're out of the house for some section of the day, and then they return, and it's also night out, so maybe there's lights on, and there's maybe the whole family's together, or maybe it's not a family, maybe it's an individual, but that's when they watch TV or whatever. But you tend to see these bimodal morning and evening peaks in people's consumption. And because it kind of has a narrative, like you can construct a narrative in your mind for why that would be the case, everybody's sort of assumed that this is basically how households consume, right? This is a good model. People work, right? They get up in the morning, they work, they come home. But as we know, we all have automated things in our lives. Sometimes one of us leaves the house and another one of us is still at home. We tend to be biased in terms of thinking, how do I do it? But you actually live often with lots of other people, or your family or roommates and so on. And so what actually happens at your house, it can often be surprising. And this is one of the things that we found. So we took 100 million load shapes from 250,000 customers, and we used an algorithm that can fit them into a much smaller number of load shapes that they're most similar to. And so we found that 270 shapes do a pretty good job at characterizing all 100 million of those shapes, right? And so these shapes have something essential in terms of the patterns of time that they're finding in people's energy usage. And I'm presenting to you the top 16, right? So this is, the 16 out of 250. And what you can see from the shapes, again, these are 24-hour patterns of consumption. You can see many of them, and including the top two, are not these bimodal distributions. This bimodal thing, morning and evening, is actually an artifact to some extent of aggregating people who have very different behaviors. And so we're starting to see there's real diversity in these patterns in time of how people consume energy, and they aren't primarily correlated with some of the typical demographic or income or climate metrics that you might expect would drive them. There's certainly some correlation, but it's not the best explanation that you could offer. And so one of the things we can do is we can classify them just in terms of qualitatively what are these things like. There's a peak in the morning, there's a peak in the evening, there's two peaks and so on. And what we find is just 14% of load shapes that are expressed in all these households follow this bimodal pattern. And this was something when, the data, I should say, that we're using on this project comes from a significant utility. And they were really fascinated by this fact. No one had ever been able to do this before, right, until this data came through. And they couldn't believe this 14% was so low. So even with something that's fairly simple to describe and set up, we're already learning there's a lot of diversity in how people use energy. And it doesn't really correlate with the things that we've traditionally used as proxies for this consumption. And so if I could sum up a lot of our work in one concept, I think that would be it. There's a lot of diversity we can uncover without without this kind of data, and it doesn't correlate with other things that we can observe. Another example, Omar also talked about disaggregation. One thing we can do is build a model of cooling energy, right? This is how a home responds to high temperatures versus low temperatures. It lets us estimate what amounts to the set point in the home that determines when they begin to cool, and the correlation with increasing energy with outside temperatures lets us say, for this house, what is the cooling energy only, right? All we see is the whole consumption. It's everything. It's the blender. It's the microwave. It's the pool pump, if applicable. But the thing that really responds with outside temperature is very likely to be air conditioning. And what we can do with that is for every household, we can estimate this annual cooling demand, and then we can order them from the highest annual demand to the lowest annual demand and add them up. And that's what this curve that we're looking at here is. And so if you do that sort, you do the biggest one first, the next biggest one second, you get a cumulative sum that represents sort of the optimal ordering of households if you're trying to access or trying to identify cooling energy. And what you can do with a curve like this is you can read off, I'm going to pull a line up off the x-axis, which is the percentile of the home that contributed to the total at that point. So we're going to pull from the 25th percentile, a quarter of homes contributed to this point. And then we're going to look off of the y-axis, which is the fraction of the total cooling energy in the entire population. And so what we're getting is 70% of the cooling energy annually is coming from a quarter of all the homes, right? So this curve is telling us that if you want to make a dent in air conditioning usage, you don't want a program that reaches everybody equally, right? You want to identify the people who are the really high consumers, and you get a bigger bang for the buck if you do it. And so what else you can learn about the households that you identify as the top 25% here in terms of their variability, maybe something about their schedule, maybe something about their overnight base load, all these other things that you can pull out of the same meter data can help you develop methods of reaching out to those people and finding a message that hopefully resonates with them and ultimately leads to action, right? This question of can our messages lead to action? And it seems clear, OPower's experience and others, the more personalized you can be without being creepy, right? This is the Amazon approach of like, instead of saying, we analyzed all of your data in excruciating detail, and we pulled in information from all these other people, and we also analyzed that, and we have all your credit card records, and this is what we think you should buy. They say, customers like you also bought, right? It sounds bad. So I think that this is sort of, this is how maybe this stuff gets presented is, households like you also consumed a lot of cooling. You should participate in a program that helps you reduce. It actually isn't creepy if you do it right. You don't need to strip away and reveal all these sensitive things. You're doing it wrong if you have to do that. And so the good news is we can learn a lot without violating privacy, without being creepy. The last application I want to talk about is this issue of model prediction. This actually, I'm also glad that Alan spoke before me. So I know Alan from way back. I did a building science degree in the same program Alan did. And Alan's a really impressive engineer. He works really hard. And his product is phenomenal. But I think you can tell how much work goes into making those models have the predictive power that they have, how hard it is, how much data you need to pull out of the building, how many other side variables you need to have access to. Alan needs a contract with that individual company. He needs to go on site, and they have a nice light footprint, and that's commendable. But the fact is, there's a real transaction that he has to do. And so if we could send Alan to every building in the country and deploy a system like his, we could sort of layer at scale these really impressive gains. But what we have instead is a more limited set of data, and therefore our models have more constrained predictive capacity. And one of the things that's really striking about residential data in particular is how poorly models designed to predict residential energy actually do from hour to hour to hour. Right? They can get the average right, they can get certain features pretty close to right. But the fact is that at the end of the day, it's individual people making decisions about their lives. Think about the things that determine within some large margin of when you come home, what you do when you're home. Do you go out to the movies, stay home and watch a movie? Those are the things that make your energy use really hard to predict, right? There's no externally available data set that's going to tell me whether you're going to be home or out to the movies on any given night. And so that's the source of error in these models. And so for individual homes, I'm finally turning to the slide now with all that background. For individual homes, outcomes, we can characterize the error in a predictive model, and it comes in at about 50%. That's hour to hour. That's roughly what the model error is. And there's many different mechanisms you can try to deploy, very sophisticated models, relatively simple models, to try to improve upon that. But there's no generalized model that can do much better than that. I'm gonna make that statement and hopefully back it up as this slide unfolds. Anyway, the error is the y-axis in this plot. On the x-axis is the total hourly energy consumption of the group that we're analyzing. And what we're going to do on this slide is look at the effects of aggregating many people together and analyzing their aggregate signal on the error associated, or on the error, yeah, the error from a model trying to predict the increasingly aggregated consumption. So both axes are log scale. But anyway, we've labeled the energy consumption of a single home, which is way down there in the left corner, and of a small business, which is not far off. And so you can see we're going all the way from the individual all the way out to kind of a large-scale feeder in magnitude. So if we take all the data that we have access to, and we can do samples that aggregate, and we can aggregate by zip code, by climate zone, by by random selection, we generally find pretty much the same pattern, which is that the error rate declines the more people we're putting together. And as a mental model, you could say, well, maybe you go out to the movies, but your neighbors stay home, and when they're out to the movies, you're going to stay home, and so things have a way of averaging out, right? That kind of, you get home early from work, they get home late from work. But what's very interesting is that it only goes up to a certain limit, and then the error rate stabilizes and flattens out. There are things that don't just average out when you aggregate. Things aren't completely uncorrelated from one another across households. And so what we see is there's declining returns to aggregation. The higher you go in aggregation, the less you're going to get out of aggregating even more. And so this red line that's labeled as no bias, that's basically what you would expect if all the unpredictability was random and the households had no correlation with each other. Eventually, you'd average out all the problems, and if you could take this enormous sample, you'd have a really accurate estimate. Instead, you start to see the blue curve, which is the fit to the data, the aggregated actual data, which is are these green points. You can see that it kind of has this bend to it, and it's flattening out. It's not pursuing zero. It's stabilizing. And if we take it out from this is 100 megawatts. If we scale it instead out to the gigawatt scale, and we add references to peer-reviewed modeling efforts, which are just the numbers on these plots, you can see that overall, people who have tried to work on this problem, the problem of prediction, people in very good journals with very good pedigree, would tend to agree with the general levels of error we're seeing at the different levels of aggregation. And one thing what's very interesting about this is, okay, so what we've learned is feeders are more predictable than individuals. Okay, there's lots of people in the power system world who could tell you that. But what we've also learned is that things that are a couple orders of magnitude smaller than feeders are almost as predictable as feeders. And what that suggests is we actually still have a pretty free hand to do a lot of segmentation and targeting and selection of customers that when aggregated have a very small model error, right? And so basically there's this opportunity to approach the accuracy of these large-scale system forecasts, but with populations that we select for very particular reasons. And so this makes us pretty optimistic that methods like targeting and segmentation can be deployed with fairly, let's say, well-constrained predictions of the outcomes. And that's actually really good news for a grid that has these operational and integration challenges. And so
so I'm going to pause you right there.
Technical work, yeah.
Because I think we're right at the line.
Yep.
So I'd like to thank all of our panelists. And if you have questions afterwards,